Hello, welcome back to the classroom. We are back at explaining the exam. So this is for Module 6 Inquiry Question 4. This is the 2019 Question 26 independent paper. Let's have a look at the question. It's worth 4 marks in total. And it says, consider a strong magnet suspended from the ceiling, moving in a circle just above a thin copper disc, resting on a sharp pivot point shown in our diagram here. So we have the string, okay? We have a really strong magnet and it's swirling around a copper disc that's free to move on a needle. The magnet rotates anti-clockwise above the edge of the disc. The disc sits on the pivot point, and from the indicator of this, I assume these dotted lines indicates the moving magnet. In terms of principles of physics, okay, so that's what we need to look into. Describe, explain what happens as the magnet rotates above the disc. Okay, so describe is obviously to indicate any features, so any observations and features. And then our explain is what causes or why does the observations occur? So why does the observations occur? So that's what we're looking into, specifically the magnet rotating part there. So why don't we talk about what should we see, and then we'll explain it in terms of the physics principles. Okay, so I'm going to firstly write down observation just to make it really clear. Observation. Okay, as the magnet rotates, the disc will rotate in the same direction as the moving magnet. Now this is actually an example of an AC induction motor, if you want to think so like that, or just an induction motor in general. As the magnet is rotating, we are going to generate some changes in flux. So there's going to be some change in flux, and what we noted before is if there's a change in flux, there is going to be an induced EMF. And if we have an induced EMF, we are going to get some eddy currents. So some induced currents, eddy currents in this example, and those eddy currents is going to generate a magnetic field that's going to oppose the moving magnet, and obviously because it's not capable of pushing back on the magnet as the magnet continues to rotate, the plate will need to rotate with the magnet in order to maintain sort of that contact of pushing it backwards. Okay, so this is essentially how an induction motor works. So this is a model of an induction motor, so to say. So as the moving magnet. So let's go down to the explanation. So explanation. Okay, so as the moving magnet causes a change in flux, on the copper disc. Okay, this will induce, so disc according to, so from Faraday's law, an EMF is induced. Producing current, in which case, according to Lenz's law, the current generates a magnetic field that will oppose the original motion that caused it. So the current will generate in this case the motion of the magnet. To oppose the original change in change in the magnetic field, magnetic flux caused by the moving magnet. Okay. Okay, so the final part that we can probably work out is the direction of the eddy current and what's happening here. So let's have a look at the diagram. We have a magnet that's going in this direction here. Okay, so as the magnet is going to the sort of this anti-clockwise direction, let's work out which direction the eddy currents are going to move. So if we have a north pole moving in sort of this direction here, we want to generate eddy currents that generates a north pole going in the opposite direction to oppose this motion. So what I want you to picture is, if you're looking at it from a sideways point of view, remember, according to our understanding of north and south pole, magnetic fields always go from north to south. So you can imagine the magnetic field sort of looking in this kind of picture here. So we're actually getting the original motion, we're increasing the amount of magnetic fields going into the page. Okay, hopefully you see that color. What we want to do though is the change, and I'll also do the change in flux we're trying to achieve. We want to cause it to go the other way. So if the magnetic fields are coming into the page as we are making this magnet come in this anti-clockwise direction, we want to cause a change that goes against it. So imagine we're going to make a north pole coming out of the page on where this motion is. So we're going to try and cause a magnetic field that comes out of the page to push this magnet away from us. Okay, so that means that according to this, thumb must be pointing up. Use your right thumb, use your fingers. Okay, so have your finger, or have your right hand, sorry, you're next to the north pole that we have here. Imagine as the north pole is coming along, the magnetic fields are going into the page, so we're going to create, or that's going to induce a magnetic field that comes out of the page to try and push it back, okay, in a way. So that means our thumb points up. The fingers, as you can see if you're pointing out of the page here, your fingers, your right hand fingers, are rotating in an anti-clockwise direction. So we're going to generate eddy currents. Hopefully we have a nice color to depict it. We're going to have eddy currents that rotate in this particular direction as the magnet is coming through. Ooh, that might not be the best color, but that's what we have. So we have eddy currents that are going to rotate in that particular direction to oppose it. On this side, as the south pole is leaving us, then that would mean, so if we have a south pole, so that means we have a lot of going out the page, so we want more out the page coming out, so we'll also see a similar sort of eddy current occurring in this sense here as well. Okay, so we'll actually end up getting fields trying to all come out the page in a way, because we want a north pole to try and drag this south pole back. We want a north pole here to push this north pole away. Okay, so let's try and work it out. I'll even do it in a slightly more fancier color just to end this explanation. So direction of eddy current, or of eddy currents. So to oppose the north pole, so to oppose the north pole moving, let's say on the disk, anti-clockwise, in this scenario, eddy currents will rotate anti-clockwise, will rotate anti-clockwise to repel the magnet as this generates a north pole. So that generates our north pole. We can also just quote that we use the right hand grip rule. As our indicator. So that's our little indicator there. To attract the south pole, we have the eddy currents also moving anti-clockwise. Right, so that causes the attractions there. Okay, so the last bit I guess we can end up saying is back up here with our explanation and observation, is that because the magnet is free to move, so as magnet is free to move, the force from the disk cannot hold its motion, cannot prevent the magnet's motion, hence the forces of interaction causes the disk to rotate, causes the disk to rotate with the moving magnet. And so that explains to us why that occurred. Because of these formations of these eddy currents, and because of Newton's third law. So this is an example of Newton's third law of motion. as we exert a force onto the disk, or as the disk exerts a force onto the magnet also exerts a force onto the disk as well. So as the disk is trying to pull and push the magnet back, the magnet is also pushing and pulling onto the disk to make it rotate. So it's caused by the induction of eddy currents on the disk and the continuous motion of the magnet is what causes the disk to rotate. Now obviously this explanation is quite thorough, so you probably wouldn't need some particular points here, but that kind of hopefully explains to you all the different concepts that come together to explain this. So hopefully that was of help to you. If you really thought this video was helpful, always, give it a like. Anyhow, enjoy the rest of your day, and if you like science, keep watching more videos.